So just so you are aware, I've started recording now. So anything that you say is on the recording. Make sure you are quiet at this time. Yes. I'm sorry? An exam. General paper, I believe. All right, so let's go ahead and get started. Drawing Lewis structures. This is a review. First step, what you're supposed to do is put which of these elements in the middle. Do you remember? Which one or is it? Carbon. Remember, never put hydrogen in the middle. Never, ever, ever. If you do that, you may as well just count yourself in half, for this test, because you cannot put hydrogen in the middle. That is like a cardinal rule. So carbon goes in the middle. Ta-da! What's the next thing we do? How many? It's a specific number. We have to take account of how many it says. It says 4 hydrogens, so we've got to place 4 hydrogens. And you imagine the carbon is having a left side, a right side, a top, and a bottom. So you fill each side with 1 hydrogen, like so. Then what? Valence electron. You can't miss this part. Carbon has how many? It's on the board, right? 4. Hydrogen has 1. And then the final thing to remember is that singles, they always single. So the 2 electrons there, they're going to connect and make a covalent bond. These 2 are going to connect and make a covalent bond. And it goes like this. How do we know that this is the correct structure? Like, if this is right or wrong. What's our proof? Go ahead, Ansel. There's no single electrons. By the way, if there were single electrons in a more advanced chemistry, we learned that that's something called a free radical and something dangerous, but not stable, right? So in this class, we're only looking at what's stable. And so this is stable, right? Octet rule is satisfied, meaning hydrogen feels like it has 2 electrons because it's sharing these 2. It's like its nearest double gas helium. And carbon, you count 2, 4, 6, 8. It feels like it has 8 valence electrons, and that's how we know the carbon is stable. And so this is good. Second one, CH3. And remember, if you see C with what looks like it's an I, it's not. It's chlorine. Just to remind yourself that. This is CH3 and then 1 chlorine. How do we draw this one? What do we start with? Put in the middle. What do we put in the middle this time? Carbon again. Remember, it's generally speaking the first element listed. Unless the first element listed is hydrogen. So carbon goes in the middle. Remember, it has 4 sides again. So this time it's just going to be 3 sides are hydrogen, and 1 side is chlorine. This is the way to approach it. And so carbon still has 4 valence electrons. Hydrogen has 1. Chlorine has how many? 7. 1, 2, 3, 4, 5, 6, 7. Like this. 1, 2, 3, 4. And everything is satisfied here. This is good. Does this ring a bell? Remember how to do this? All right, this starts our fundamental basis of where we're going in this unit. Today we're going to learn how to draw organic molecules of hydrocarbons, meaning just carbons. Today we're only looking at 2 elements, carbon and hydrogen. We won't expand to other elements until at least next week. We will just be looking at 2 elements on the whole entire periodic table for the next several class periods. So first of all, what is organic chemistry? What is the scary science that people talk about? It's actually, we learned this at the beginning of the year. It's the study of all compounds that have carbon, except for 2 specifics. Carbonates, do you know what those are? CO3, 2 minus. You may want to fill that in for yourself. Organic compounds, the study of all organic compounds with carbon, except carbonates and carbon oxides. These are the only ones not classified as organic. So basically, if I see carbons and hydrogens, it's organic. So right here, this is a fuel we'll learn the name of shortly. It's actually the one that's in your Bunsen burners, the ones that we've been using throughout the year. It's this molecule that we burn, actually. And then this, you know, it's one of a lot of people's favorites because it's glucose. Glucose is sugar. If you like sweets, you like glucose. What? You're enjoying some glucose right now. Good so far? So, study of carbon-based compounds. If it's got carbon in it, you can assume that it's organic, with very few exceptions. all of our biomolecules, like carbohydrates, proteins, lipids, they're all organic chemicals. If you study biology, you will be studying a lot of organic chemistry. So what career fields directly use this study? If you go into agriculture and food, you will need to know about organics. Biotechnology, medicine, of course, like you saw in the video, oil and petroleum, personal care, that's actually like cosmetics and shampoos. There are people who make formulations for that, organic. And then even in the water industry, there's organics in the water that can be cancer causing. What industries hire specifically organic chemists? Biotechnology, pharmacy for sure, that's a big field. A lot of people study organic chemistry. If you want to be a pharmacist, you have to know organic chemistry very well, because that is the foundation of that whole entire field of study. It's the study of producing medicine, making drugs. Chemical industry, so this is like different industries such as the manufacturing industries actually use a lot of chemistry, organic chemistry in it, and even in production of different drugs and medicines. Consumer products and petroleum. So even like paints, different formulation of paints, it's all chemistry and reactions that make different paints. People who do that. So simplest organic molecule is called hydrocarbon. And if you break down the word hydrocarbon, these are molecules that have two elements. Guess what they are? Hydrogen and carbon. So hydrocarbons are any molecule that has just hydrogen and carbon. That's all it is. So the simplest organic class of compounds, we call these hydrocarbons. They're organic compounds. They only have two elements in them, carbons and hydrogens. If you see any other elements, oxygen, nitrogen, chlorine, fluorine, it is not a hydrocarbon. By definition, hydrocarbons only have carbons and hydrogens. We're only looking at hydrocarbons for the next several class periods. And today we're only looking at hydrocarbons like these. Straight chain hydrocarbons. What are hydrocarbons like? First of all, hydrocarbons are non-polar. Do you remember that word? Non-polar. What was non-polar? Uh-oh. Non-polar covalent. What does that mean? Electrons are shared equally. Electrons, so you may want to write that to remind yourself. Electrons shared equally. No charges. No partial positive charges, no partial negative charges. A way to tell that you have something nonpolar is that it's symmetrical. Does this molecule look symmetrical to you? It is. So this is a symmetrical molecule. It turns out, whether symmetrical or not, all hydrocarbons, so I should add the word in front here, all hydrocarbons are nonpolar. This is because of the electronegativity difference. Uh-oh, words from the past. You remember that word, electronegativity? It's been a while. The electronegativity difference between carbon and hydrogen is very small. Carbon has an electronegativity value of 2.5. Hydrogen is 2.1. Even if this is not a symmetrical molecule, if you subtract these two, what's the difference between 2.5 and 2.1? 2.5 and 2.1. Subtract those two numbers. It would be 0.4 is the difference. Remember that anything between 0 and 0.4 is always non-polar. This is like stuff from the past. 0 to 0.4 is non-polar. 0.5 to 1.9, polar. And above 1.9, do you remember what the last classification was? If it's superpolar, what do we call it? Ionic. So it's either electrons are shared evenly, electrons are not shared evenly, they're shared but not evenly, or they're not shared at all. If the difference is above 1.9, we call this ionic. I'm reminding you of all this just to tell you, because carbon is 2.5 and hydrogen is 2.1, the difference falls within nonpolar. So whether symmetrical or not, all pure hydrocarbons are classified as nonpolar. What does this matter? This tells us that they have weak intermolecular forces. These are words from the past too. What does that mean? They exist as gases and liquids. This is a molecule you may be familiar with when I say the name. Have you heard of propane? Where have you heard of propane? This is propane. If you've watched King of the Hill, the old cartoon, Hank Hill is a propane salesman. It's a gas used for lawnmowers. They use it for lawnmower fuel. But it's gas, right? It's gasoline. To exist as a gas, it has to have weak forces of attraction. To have weak forces of attraction, it has to be nonpolar. Nonpolar molecules have weak forces of attraction. And this causes them to be gases or liquids. So you'll notice, one of the things you're going to notice about these hydrocarbons is they're usually fuels. We use them a lot of times as fuels. Fossil fuels. All right, so if I took gasoline or oil and I mixed it with water, would it mix? Think about it. I have some oil here and I have some water. Do these two mix? Some of you know this off the top of your head. I got myself some water, got myself some oil, right? Do these two mix together? What will happen? They separate into two layers, right? Why? Why do they separate into two layers? That's what's here. Oil and gases are nonpolar. Water is polar. You may remember this from the past. If the polarity is not the same, they don't mix, actually. Polar things dissolve in polar things. Non-polar things dissolve in non-polar things. Oil and water will never mix. Oil is on the top. Why? Remember why oil would be on the top? It's a lighter density. So oil is on the top because of a lighter density. But the reason they separate is not because of density. The reason they separate is because oil is nonpolar, whereas water is polar. I'm going to show you real quick what the oil molecule looks like. You know. That's what I mixed with water. That's the molecule. What do you notice is the big thing here? Lots of carbons in. Hydrogen. It's very, 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 very. It's got a big nonpolar segment. It's got a small polar segment, notice. But most of it is nonpolar. And because most of it's nonpolar, it will not mix with water. That's the general idea here. All right. So today, we're going to go over some types of hydrocarbons, and we're going to learn how to draw them correctly. An alkane, by definition, is the first type of hydrocarbon you need to know. We call them alkanes, and this is going to help inform us of their names, how to name them. This is a hydrocarbon where you only have single covalent bonds between carbon atoms. So if I see an alkane, this means all my carbons have to be single bonded to each other. There will actually be two other types of hydrocarbons, and I'm going to tell you them now, because although they come in a future lesson, you can memorize them together. The other two types of hydrocarbons are alkenes and alkynes.
Pardon the interruption, teachers. At this time, if all the seniors can report to the auditorium and please sit in the back section of the auditorium. All seniors, please report to the auditorium at this time. Any teacher with all senior classes, if you could please come down to assist. Thank you.
You're doing graduation rehearsal. Alkane is when I have carbons that have single bonds only. An alkene is when I have at least one carbon in my structure that has a double bond. I want to write this down. And an alkyne is when I have at least one carbon-carbon triple bond in my structure. And there's an easy way to memorize this. That's what I said. I'm going to tell you them together because there's an easy way to memorize this. Think about it like this. This is one bond. 2 bonds and this is 3 bonds. Alphabetically, A comes before E, which comes before Y. So there's this old song, like 50 years old, that goes A, B, C, easy as 1, 2, 3, and you can memorize it that way. A, B, C, 1, 2, 3. Alphabetical order. Alkanes, 1. Alkenes, 2. Alkynes, 3. So easy way to memorize that. And that's why I'm giving you this now, although these are going to show up on a different lesson. Because they're easy to recognize once you get the idea. All right, so far so good? All right, you're going to be 3 different types of formulas. The first type is called the displayed formula for an organic molecule. The displayed formula is the Lewis structure, so you want to write that underneath. Displayed formula equals the Lewis structure. All covalent bonds and pairs of electrons are shown. And the difference between the 3 formulas you're going to learn is how much we start to hide. So, what do I mean by that? You're going to get exhausted of writing all the atoms in organic molecules. So people developed ways to write it quicker. You know how there's shorthand notation, or how you guys like to use text speak, like TTYL for talk to you later, that kind of thing? We can shorthand this as well. And that's what you're going to learn, is how to shorthand organic molecules. That's part of what we're going to learn in today's lesson. So the first type of formula is called the displayed formula. This is the type you're already aware of, where you have to draw out every single bond, and you ensure that you follow the octet rule, and you can just count it up to be sure. It's called the displayed formula for an organic molecule. The second type of formula is called the structural formula. And so I'm going to, for the same molecule, this is the displayed. Let's talk about how to turn that displayed to a structural formula. In a structural formula, we collapse all the single covalent bonds. We just don't write them. And what you do is you gather all the hydrogens and any other groups, for now we're just talking about hydrogens, that are connected to each carbon in your chain. So notice here, this molecule has how many carbons in it? Got 4, right? So you would look at your first carbon. You can circle it here. How many hydrogens does that carbon have? 3. So instead of writing C, line to H, line to H, line to H, you can write it as CH3. Does that make sense? This can be written like this. And then we move to the next carbon. This carbon has how many hydrogens? So we write it as CH2. Yes? The next carbon has how many hydrogens? So we write it as CH2. And the one on the end here has? So we write it as CH3, which you'll see was on the screen here, the example of the structural formula. So this is the same molecule written, condensed a little bit. Instead of writing all the single covalent bonds, we're like, we know they're there. We'll just tell you how many hydrogens are in each carbon. There's an even more condensed version of this that you're allowed to use, that Cambridge accepts. And so you can condense this even further. So condensed. And you can group anything in the middle. So let's say you had 5 of these, right? You can group them together as different units. Let me explain. You could write this as CH3, parentheses CH2, and then just count how many you have. How many of these CH2s do you have? 2. So you would write 2 on the outside of the parentheses, and that's how you have 2 of them. And then CH3. And so if you want to save yourself a little bit of writing, you can condense it even more. Both of these are accepted by Cambridge. Both versions accepted by Cambridge. And both versions are used by Cambridge in different questions, so you should be good. I'll give you a little bit of time and then we'll continue. And so the displayed is the entire Lewis structure. The structural formula is taking the Lewis structure, the display structure, and just writing how many hydrogens belong to each carbon in the chain. And then there's going to be an even smaller way, a really quicker way to write these. Yes? This said both versions accepted by Cambridge. So Cambridge is okay with you writing structural version this way or this way. And they'll present either way to you. Usually they'll do the one on the bottom because they like to write less too. All right, so far so good? So this is format 2. Format 3. And this is what I had just said about the extra condensed version. For every CH2 in the middle, you can just use the little n to say how many you have. The third version, to most people, is the weirdest at its first outset, but once you understand it, is the easiest. It requires the least amount of writing. This is actually the way that if you looked in the front here, this is the structure that's often used by most people to describe organic molecules, just a bunch of lines. And so here's what you need to understand. At the end of every line segment is a carbon. So this is a carbon, this is a carbon, this is a carbon, and this is a carbon. So at the end of every line segment, in these zigzag lines, you have a carbon. In the skeletal formula, hydrogens aren't shown at all. You just know they're there. So all hydrogens connected to carbons are not shown. It is implied they are there. So you would have to understand, if you look at a skeletal formula, that this carbon here has one covalent bond coming out to it to another carbon. How many hydrogens do you think this carbon has? Every carbon has to have a total of how many bonds? 4. If one of them is being connected to a carbon, what about the other? They have to be connected to hydrogen, right? So this would be a H and H and a H, and you have to understand that in your head for the skeletal form. So how many hydrogens would be on this carbon in the middle? Because there's 2 bonds to other carbons, there would have to be 2 more bonds to hydrogens. So basically, hydrogens fill up the rest of the molecule until every carbon reaches 4 bonds. And that's one of the main ideas of organic chemistry. You've got to know carbon has to meet its 4 bonds. So this would be 2, this would be 2, and this would be 3. And this is actually the same exact thing as this is, right? The same exact molecule, which is the same exact molecule as this is. So displayed is like this. Structural is like this. And skeletal is like that. Now, when you take your final unit exam in your written portion, there will be some questions where you have to write a specific type, and then there'll be a bunch of questions where you can pick your favorite type. If you prefer to draw displayed, you can draw those all in displayed. If you prefer structural, you can draw them all in structural. If you prefer skeletal, you can draw them all skeletal. I'll tell you, usually students prefer skeletal, but some students prefer displayed because they want to make sure that octet rule is satisfied. Make sure they don't miss anything. So these are the 3 different formats you've got to be aware of. I'm going back here real quick. Now, in the next few slides, we're going to do some practice questions with these different formats. I'm waiting, I'm giving you a few minutes, and then we'll continue. Or a few, 30 seconds. You're good? Okay, Jake? Okay. So, here we go. Draw the display formula, the structural formula, and the skeletal formula for the straight chain straight just means all your carbons are in a row, if you want to write that up. If they say straight chain, this means all carbons in a row that have 3 carbon atoms. So how would we write the display formula for an alkane that has 3 carbon atoms? What will we start by writing? Go ahead, Arista. 3 carbons. So go like this. Carbon, 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 and connectors, because they're bonded to each other, right? So after we have that, what do we do for the display structure? If the element isn't carbon, what is it? For hydrocarbons. These are alkanes are hydrocarbons. If carbon is not connected to carbon, carbon is connected to what? Hydrogen. So every other one of the 4 bonds has to be connected to hydrogen. So how many hydrogens would I write on this carbon on the left-hand side? 3. 1, 2, 3. You basically fill the molecule with hydrogens until you get to 4. You need me to get back in? Okay. Check what it did. After 3 hours, it Sabrina, it's good, right? Okay. So, start again. 3 carbons. 1, 2, 3. On the left-hand side, that carbon is connected to 1 carbon. That takes up one of its 4 bonds. So you gotta be able to, I said there would be a little math here, but you gotta count to 4. So, carbon has 1 bond with carbon. How many hydrogens does it need to fill all of its bonds up? 3, right? 1, 2, 3. The carbon in the middle gets how many hydrogens? Because it's got 2 bonds, so it needs 2 more hydrogens to fill up. And on the end here, 1, 2, 3. And if you miss 1 hydrogen, it's wrong. And Cambridge counts it wrong if you miss 1 hydrogen. That's why you gotta be so careful here. Now that was displayed. What's structural? I taught you what structural was. Do you remember what to do? Every carbon, you write all the atoms that are connected to each carbon in the line. So the leftmost carbon, what would you write? C, and instead of writing all the bonds, you just write 1, 2, 3 hydrogens attached. So you write it as CH3. Yes? The next one in the line, you write as CH2. And the last one here, you write as CH3. That's structural. Yes. Yes. The what? Oh, you don't need parentheses because there's only 1, right? So you don't need to put a parentheses with a 1. You can if you want, but most people will not do that unless you're condensing more than 1. I wouldn't do it myself. Yeah, I'm trying to erase it because I don't want you to do it like that. I'm just saying you could, but I don't want you to do it like that. Skeletal. hydrogens at all. So in the skeletal form, the C molecule would be this. Is that what you got? And you're supposed to interpret from this that at the end of each of these lines is a carbon, and looking at how many lines each carbon has coming out of it, you figure out how many hydrogens it has. That's how skeletal form works. All right. So now it's your turn. First, Dan. See if you can do this for 6 carbon atoms. I want to see your display, your structural, and your skeletal. So first stamp, I'm leaving this on for about 3 minutes, 4 minutes. I'm checking in on you to see if you're good so far with what we've done. Once you have it, raise your hand. Now check off that you did. Very. If you have the answer, just let me know. Raise your hand. You've got a few minutes. Keep working on it. So your phone away. Yep. I told you it will hurt your hands eventually, right? That's why we have the other way. Display gives you the most information, but it's the most tedious of the three. Beautiful. 2, 3, 4, 5, 6. Just erase that one right there. One way to help you with skeletal is to put like a little dot on each end. 2, 4, 5, and 6. This is structural. All right, once you have it, raise your hand. Ready? And then we just make the skeletal. No, it just didn't have it. Here. I'm talking individual person. You're missing something else. Every single like end of a line. Yes. Well, CH2 and then a 4 on the outside chain. H2 on the inside. Yes. Got it? 1, 2, 3, 4, 5, 6. Yes. You're reaching up to the sky. Perfect. Ready, wait a minute. Yes. Yes. 2, 3, 4, 5, 6. Very nice. Good so far. Good so far. Wow. Ready? You're missing one hydrogen. All right. Anybody else for me to check? You've got about 1 more minute for me to check before I move on. What happened? Whoa. 1, 2, 3, 4, 5, 6, 7, 8, 9. The ends also counts. That's no need. Jamie? What is that at the end? I can't hear Carl. All right, 30 more seconds. You don't fill in the hydrogen. You can do that to check so you don't have to. Yes. Check again. No, you're good. Yes. Please. Go ahead. You ready? Yeah. Erase one on your skeletal. And you shouldn't show any hydrogens on your actual skeletal form. All right, I'm moving forward at this time. So, the last big thing for the day is the memorization thing. So don't freak out. You do have to learn how to name organic molecules in this unit. That's going to be one of the major things you need to do. Besides drawing them, you're going to need to learn how to name them. And so your goal in the first lesson to memorize is how to name your alkanes based on how many carbons are in the chain. So here's what I want you to do. Underline the prefixes meth, eth, pro, bute, pent, hex, hept, oct, non, and dec. These are the prefixes for the amount of carbons in the chain that you are going to need to memorize. So 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5, 6, 7, 8, 9, and 10. These are the prefixes for how many carbons are in your chain. These do need to be memorized. I know for some of you that will be bad news, because you do have to know the official rules. These are called the International Union of Pure and Applied Chemistry rules for naming molecules. And so the good news is that, first of all, you should already know factor from geometry from earlier this year. When you named molecules covalently, we did pent, hex, hept, oct, non, and dec for our covalent names. So these you should already have. So the new ones to use should be meth, eth, prop, and bute. Methane, ethane, propane, and butane. And so some of you, your minds might be wandering. You're like, wait, you said meth. Have you heard of meth before? Anywhere? Like in a illicit sense? Like it's a drug? Methamphetamine? The meth and methamphetamine comes from the fact that there's 1 carbon hanging off of the chain somewhere. That actually is what that name comes from, is that it's 1 carbon hanging off the chain somewhere. In a future later class, in an AICE class, you'll get to look at the structure of it, the chemical structure of it, so then you'll be able to analyze it actually. But that is where that name comes from, if you weren't sure. That's what methamphetamine comes from. But anyway, to get rid of that elephant in the room. But methane is also a natural gas. If you've ever heard of natural gas, which is about 20% of your gas production in the United States of America, that's methane. That's CH4. Methane is a big deal around America. Methane. Methane is not methamphetamine. Those are 2 different things. Methane is just CH4, 1 carbon and 4 hydrogens. Now you would have heard me call it back in the day of covalent compounds. I would have probably called it carbon tetrahydride. But actually, the organic name is the one most people use. So from now on, if you see CH4, that's methane. If you see 2 carbons, it's ethane. So on and so forth. And you're going to see as we go through this unit, a lot of the molecules you're going to recognize. They're going to come up that people use these terms for things that we actually use. So, like methane, like I said, natural gas. Propane is used in lawnmower tanks, and I mentioned butane. That's what we use in our Bunsen burners. So, like the burners that you use for the 3,000-degree fire that could, like, burn your face off, which you would never do. That gas is butane, right? All right, so bad news you have to memorize. 1 is meth, 2 is eth, 3 is prop, 4 is bute. I have an acronym to make it a little bit easier. So here it is. You want it? Monkeys eat peeled bananas. And there's the order for you. Meth, eth, prop, bute. Monkeys eat peeled bananas. Remember that acronym. It's a mnemonic device to help you to get the order right. Meth is 1, eth is 2, prop is 3, and bute is 4. So you do have to memorize it, but there's an easy way. Monkeys eat peeled bananas. Meth, eth, prop, bute is 4. And then the others, like I said, But 5 through 10, you should already know. And if you don't, then go back and actively work on memorizing those prefixes because they're useful here too. In the pre-ACE course, you will be memorizing all 10 of these. In the ACE course, you would only actually have to use 1 through 6, just FYI. They only go through HEX in the ACE course. But in this course, you're going to learn 1 through 10, all of them. All right, so the simplest straight chain alkane that exists is actually ethane. Because for you to have an alkane, remember alkane means you need a single bond between 2 carbons. Ethane is the simplest one you can have because methane doesn't have 2 carbons that connect. So this is the simplest straight chain alkane. Straight chain means carbons are in a row. Anytime you have a repeatable increment, the next thing you're going to see, we call this a series. So, for example, remember when I told you that you could take this and turn it into this? And if you have this, do you really want to write all this out? Instead of writing all of this, 1, 2, 3, 4, 5, 6, 7, 8, you could take these 6 CH2s in the middle and write CH3, CH2, 6, CH3. The difference between these molecules is just that you keep adding CH2s, right? CH2, 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 CH2. This is what we call a series. It means that these molecules are connected. They have the similar molecular structure, but they just have a constant increment of change, meaning add CH2, add CH2, add CH2. This is the alkane series, which is just carbons and hydrogens. And so that's being said here. A homologous series is basically just your series of molecules. They're the same thing, except for one has more CH2s than another in the middle. They just have the same increment of change in between. All right, so let's see if you've got an idea of what you'll be asked here. What is the displayed formula for hexane? Can you get a picture? What is the displayed formula for hexane? So you're going to be asked, given the name, you're going to have to draw it. Well, you have enough information here to figure out how to draw this. You've got to know the prefix hex. Oh, what does that mean? Hex means 6. Alkane at the end means all of my carbons are single bonds. So what do I need to do here for the displayed formula? Every single bond has to be shown, right? So what I need to do is 6 carbons in a row to start. 1, 2, 3, 4, 5, 6. So far so good. 6. Not terrible, not satisfied. We gotta fill it up with hydrogens, right? Until every carbon has 4 bonds. So this carbon on the end has 1 to another carbon. How many hydrogens does it need? Could you just draw the conclusion that the carbons at the end need 3? And the carbons in the middle, if it's a straight chain, always need 2? Sure you could, because you're savvy. So you just fill up until every carbon has 4 bonds. It's tedious, but hopefully not too difficult. And this is the displayed formula for hexane. You get the point here if you got this as your answer. I have another question. This is going to show up on your homework today. How many single bonds are here? This is a good question I'm going to ask. How many single bonds are there here? Why don't we address it? Because I know I asked it in the homework. So what would be the best way to go about doing this? I'm going to tell you my strategy. I would pick a different color, and I would just start, like, counting. 1, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Because remember, it's the bond between those. You can't double count, right? Another way I do it is just to put a line through it. I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that way I know which ones I've counted and which ones I haven't counted. That's one way that I'll go about it. But the answer here would be I'm going to ask this in your homework. The one, yeah. You could. You can come up with a strategy to make it simple. All right, structural formula for heptane. What do we do here? Omar. So start with your 7 carbons, right? Hept means 7. And are you going to have to memorize that? A means single bonds between those carbons. So you've got 7 carbons. 1, 2, 3, 4, 5, 6, 7. Now remember what I said about structural formula. You're actually not supposed to show the covalent bonds. So what could we do here? What nifty way could we do this? How many hydrogens does each carbon on the end have? 3, right? And the ones in the middle have 2. So CH3, CH, notice how I changed that, the single covalent bond to a hydrogen. CH2, 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 and CH3. Or, if you didn't want to write all that, you could have recognized that because there's 5 CH2s in the middle, if you recognize that in advance, this is the same as that in condensed structural formula. Remember, Cambridge accepts either of these. Yes? Okay, skeletal formula. For octane. What do we do here? Oct. 8. 8 carbons in a row. But we don't actually draw the letters for skeletal, right? We just draw them as ends of line segments. So here's how to count them. This is already 2 because a line is has 2 ends. So this is 2. If you're unsure, you can put a little dot at each end to help yourself keep track. This is 2. Then you zigzag. 3, 4, 5, 6, 7, 8. Some of you might be wondering why we zigzag. If you didn't want to know why, it's because they're tetrahedral. The shape of 4 carbon with 4 bonds is tetrahedral, and it would be zigzagged. But it also makes it easy to count if you zigzag it. So that is the actual shape between the atoms. That's how they're connected. I'm not testing you on shapes and bond angles on the test. You're welcome. All right, how are we feeling about this? Okay? You've got one more set to do yourself. So I've shown you how to do display with a name, structural with a name, and skeletal with a name. So for the last stamp of the day, I told you on most lesson days you could earn 2 stamps. For the last stamp of the day, you've got to do display formula for ethane, structural formula for butane, and skeletal formula for no name. So once you have those 3, show it to me, and I'll go ahead and give you the stamp. And ethane.